So, hi everybody. I cannot be with you in person today. So, for this reason, I recorded this video containing the contents of the second part of research design for psychology. And last time we finished the session talking about experimental validity. And let's define that again. So validity of an experiment is the measure of the interpretability of evidence and the truth of inference. So it is multidimensional. So there are many aspects of validity you have to consider. And when comparing different studies with each other, you observe that different experimental designs have our emphasis on specific aspects of validity. There is no perfect design in which you are able to maximize all aspects of validity simultaneously. And so this is the main reason why usually you need different experimental designs to develop a research agenda and produce better evidence. So, why is that so? Because the kind of measurements you have to take to increase one aspect of validity usually will have negative consequences on other aspects of validity. And so by trying to investigate a specific research question using a specific technique will optimize your design to increase specific aspects of validity, but almost forcefully it will decrease other aspects of validity. But when you have a landscape of different experimental designs, so you use different techniques, you address different populations, and you use the different tasks, so to make your measurements, you are able to combine the strengths of different designs and produce a solid ensemble of evidence. And so you may always be critical of research fields which are too strongly based on just one single kind of experiment. And so always be aware of that. So a strong, a solid research field always is founded on the use of several complementary designs. Yes, but let's move now to the characterization of different types of validity. We may distinguish between two main aspects of validity. So the internal validity and the external validity. And internal validity will be subdivided again in specific subtypes of validity, as well as external validity. And in the rest of this session, we will discuss different aspects of internal and external validity. And what is the definition of internal validity? So it is defined as the quality of the choices you make when you build your experimental design. And it involves properties of measurements. So are the measurements you're taking precise? Are the measurements you're taking representative of the theoretical constructs you want to address? It also involves question of sampling. Are you sampling adequate? And also the kind of statistical tests and descriptive statistics you use. Also other aspects of design like personal interactions, so between experimenters and participants, and also between participants themselves. It also includes model diagnostics, so that means all the quality level diagnostic tools you have to investigate. So how well your experiment worked, and so whether any assumption behind the use of specific statistical tests have been violated, and if they have been violated, most of the time we violate specific assumptions behind these tests, but how severe is the degree of violation and which consequences does it have to the interpretation of the results. And so sometimes you may expect severe consequences which may mess up so the whole interpretability of your results, but in other cases it's not so bad and you still can learn a lot from your results. And so model diagnostics will tell you more about that. So it's a really important aspect of the statistical validity of an experiment. All right, so these are all different aspects of internal validity. And let's move now to a short definition of external validity. So the external validity is not about the characteristics of your experimental design alone, so the quality of measurements and so on, but it's rather pointing from the specific results you have had to other phenomena you may observe in reality. So it's about the generalizability of the results you obtained. And this is not granted to you for free. So only well-conceived designs which tap on the different aspects of the dependent and also the independent variables, so which make a comprehensive measurement of all their possible degrees of expression, will enable you so to achieve some degree of generalizability. So if you only measure a very specific circumstance with your design, so the generalizability will, of course, be much more limited than when you include other expressions of your variables in your design. And as you may understand right now, so usually the kind of thinking which increase internal validity may include some decrease in external validity and vice versa. And only if you spend a lot of money and a lot of resources recruiting large amounts of large numbers of people to participate in your design, you may be able to have high levels of internal and external validity under most circumstances. So yeah, so this is the kind of discussion we have earlier, that no design is perfect. So every design will give you a mix of some qualities from internal and external validities and some flaws as well. And we only hope, and so this is kind of a good practice in research, so to do whatever you can to reduce as much as you can the flaws from your experiment, because only when you exclude these flaws or confounding effects, you're able to straightforwardly interpret your results. Okay, there is no mystery there. And back to the discussion from last week. So validity as a whole is maximal among experiments providing undisputable critical evidence falsifying specific theories. So if your theory does not provide many testable hypotheses, so per definition, so it's not a very good theory. And if it's impossible to generate experiments which undisputably can falsify your theory, so then you have a problem. And so usually, so the degree of advance in scientific knowledge is measured by the falsifiability of theories. And yeah, so there's a long discussion. So just be aware that this is exactly how internal and external validity are combined, so to test hypothesis in a more general manner. Yes, so then let's move now to specific aspects of internal validity. So we may distinguish between an aspect called causal validity and another one named statistical validity. And what is about causal validity? It describes your degree of certainty when you observe a specific change in the dependent variable. So how sure can you be that it is was produced only and mainly so only by your independent variables and not by other factors. So first of all, so you have to be sure that there is an unambiguous temporal precedence between the independent and the dependent variable. So of course, the independent variables which occur or were measured later in time cannot influence the past, right? So this kind of logical thing. And in many cases, because you have a simultaneous measurement of dependent and independent variables, you may not be really sure about the causal connection between the independent and dependent variables you defined. So in many cases, it's open for discussion whether so this temporal precedence is given or not, whether so it's possible to interpret results as wished according to the conception of the design. And also aspects of selection and stratification of treatments or participants. So how much are you able to assign randomly participants to specific groups or to assign treatments to specific time points. Under many circumstances, it's just not possible. So if you want to compare children with reading disorders with other children without reading disorders, so the whole participants you will recruit, so they will have or not have the reading disorders, and all other characteristics of participants, so a history of failure in school or a history of stress while learning, and so all these personal variables connected to them, and you cannot get rid of it. And so this is an important determinant of the causal validity in your experiment. So in this case, we are dealing with quasi-experiments, and but the same logics is also applicable to intervention studies in which you have a sample of people, which then will be assigned to one of two treatments. So do the participants have any influence on their assignment to different treatments, or is that random or not? And every time it's not random, you have a problem with causal validity. So it's lower than the optimal value. In intervention studies, you also would very much like to record precisely everything happening in the data collection. So from recruiting of participants to the end of the post-test or follow-up measurements. Why that? Because you may have to deal with severe dropout during the experiment, and the subpopulation of participants continuing in the design, so not giving up and leading to missing values. So they may not be representative to the whole of the participants. And so there may be very specific and very important reasons for people to leave your study. And if they are systematic, so if they are not random, so they may also compromise your ability to interpret your results. So there is a nice example of how that works. So you see this airplane here on the up right, and you see that it's marked with small red dots. And so these were real observations of airplanes coming back from battle. And so the question was which parts of the fuselage of the airplanes should be reinforced for the airplanes to survive better battles. And if you see that so the red dots are concentrated on these regions you may see, you may feel that these are the regions you may have to reinforce for future battles. But the point is, there are many airplanes which never come back from battle, and you have no observation on them. And so actually, because you may be sure that the red dots were measured on airplanes which came back from battle, that exactly these regions where you can spot them are not as important as the other ones. So you see here, so the pilot's cabin and the two engines and the back part of the fuselage of the airplane. So actually, what you're not seeing is more important than what you're seeing. And people giving up your intervention studies may tell you more than the people able to finish it. So never forget this aspect of so dropout and selection during intervention designs. Yeah, another important point is the distinction between maturation and treatment. So it's really important when experimental designs go on for so long that you may not be able anymore to disentangle between natural maturation, development of your individuals and the effects of your treatment. Because let's say if you're measuring reading competences, and you'll be measuring reading competences over, let's say, 24 months. So within 24 months, every child minimally able to read will get better. And so this is an effect of maturation, of experience with the ability of reading. And if you want to measure the effect of some treatment on that, you may be interested in identifying how much of the changes you observe in time are due to simple maturation or simple spontaneous remission of your patients. Or any other individual you are measuring. Another point connected to that is regression to the mean. So this is a statistical, mathematical artifact of which is caused by the natural variability of measurements. So measurements you may take from people or from organisms. So they are naturally variable. Even measurements taken on the same spot, on the same organism, after negligible time interval, they will still be variable. And when you, for your design, you select people or you select groups of subjects based on extreme values. So extreme values are per definition less probable than less extreme values. Actually, if your distribution has a central tendency, so if mode, median, and mean come close together, so you have a distribution where extreme values are less probable than more central values. And because of these characteristics, so you may observe that spontaneously values which are extreme at a first measurement will be less extreme in the second one. And if let's come back to the example of reading abilities. If you select children with really very pronounced reading abilities for a specific measurement, and then you give them an intervention, you may see that they will improve a lot. But if you have a control group of children equally impaired, you see that they improve as well. And why is that? This is because, so even if according to your inclusion criteria, so you focused on relatively extremely low reading abilities, usually the reading abilities of impaired children will be a bit better than what you measure at a certain moment. And because of this natural variability, you may see that some extreme values you observed in one measurement will not be the same in the next measurement. There is a caveat here. So how much stability do your measurements have? And different measurements may have different stability. And the higher the stability you have in your measurement, the weaker is the effect of the regression to the mean. When your measurements are not stable at all, so they don't measure any trace of your participants, but only a state, so a momentarily state of your participants or subjects, you see that the regression to the mean is maximal. So you see that different measurements on the same person without any reason will oscillate a lot. So this is also an important point. So for the definition of your dependent and independent variables, so you want to have variables in your design with a certain degree of stability for you to be able to exclude extreme effects of the so-called regression to the mean. All right, another point is more based on specific interpersonal interactions. So attrition. Your participants may become angry or demotivated during your experiment. So when you have two conditions and one condition is more boring than the other one, then interpretation of your results, if you see that the more motivating condition works better, are really trivial. And if at the end you see that participants assigned the boring condition, so they leave your experiment more frequently and they are less motivated, they even may get worse during the intervention. So this is a clear sign that you have a problem with attrition there. And there are many reasons for that. So the nature of the treatment you give, or the ability of people so to know what the other group is getting, and so by means of comparison with another group, so may also observe a lot of angriness. Yeah. Test experience, so previous to your experiment, in psychological papers, you read a lot that participants were naive regarding the purpose of the experiment. And what does that mean? So that the previous experience participants may have is negligible and does not influence the interpretability of results. All right, how precisely are you able to measure that? When you recruit people from commercial participants platforms, such as mTurk or Probando, you may have problems with that because people have probably participated in similar experiments in the past and have much more insight on what you are actually measuring than you may expect. So never be naive regarding the ability of your participants so to understand what you actually are measuring. So it's never a trivial aspect of design to address. Changes in instrumentation. Yeah, there are many problems there. So when Windows just makes automatic updates to your system, or when there is a new version of a software or a new version of a specific apparatus you are using for your measurements, and then so you have a confounding there because different versions of the same software or of the same hardware may not work equally well, and so newer versions may contain bugs which the older ones do not have, or they can be more precise, more efficient than the other ones. So this can definitely change your ability to measure your values, and so this will may reduce the interpretability of your results. And beyond that, so designs which are too complex. So let's say you have 5, 6, 7, 10 different independent variables in your design, or variables you are controlling for, but not stratifying between your different experimental groups. So it's a danger because you have not only additive effects of every other independent variable you add to your design, but also interactions, and you may not be able to address all these interactions, so you may have a problem with your statistical design there. So always aim to keep your design as simple as possible, so as straightforward as possible, to still be able to accommodate the expectations you have according to your theory, but nothing further than that. And so this is a compromise every time, so by every design. So you may always be aware that the more complex your design, the more complex the spurious effects you may obtain. So the more interactive effects and unpredictable behaviors of the variables you may not be able to interpret. Yes, so from there we can move so from causal validity to statistical validity of your experiment. So what is that about? So it refers to the statistical procedures you use to measure and compare your data. And it is also made up of many different subtopics. So, so the statistical conclusion validity describes your ability to interpret the results you measured in terms of an implementation of your theory. And it's never perfect, so it's always also a question of good operationalization. And beyond that, so we also have the problem of statistical inference. And statistical inference regarding the effects of independent variables on your dependent variable may involve the exclusion of covariation with other confounding variables, and only if you are able to straightforwardly disentangle between these different sources of systematic effects, you'll be able to interpret your data. We also already spoke about type 1 and type 2 kinds of statistical errors, which happen with specific probabilities. And if you know your theory well, if you know your theory well, you will be able to take the measures so to control for both type 1 and type 2 errors. All right. We also have a problem when we conduct uh, many different tests. So when you test the null hypothesis many times, the probability that at least some of your results will be false positives, it will increase quite fast. And the probability will be much higher than the nominal value of 5%. Um, um, and it yeah so a good control for that is given by the procedures so to correct for multiple comparisons. And another point of statistical validity is your ability to have a look of your data and understand its properties before you conduct your tests. Because so we live in times where so it's pretty easy to get a specific data set and make calculations with that. So nothing is forcing you to evaluate first the properties of your data before you run some tests. But it's essential to do that, so to be able to ascertain a specific degree of statistical validity. So you should always inspect your data. So look at every cell in your experimental design. So how is the distribution of data there? If something strange happened, and if some anomaly is available in your data set, so you should be able to track where it comes from. So are they real data or are they mistakes during the recording of data or labeling of data? So everybody commits mistakes. It's just a question of time. And the more complex your design, the more important it is so to control for the quality of your data. And beyond that, so the quality um, management measurements you may take. So they involve, under some circumstances, so Bayesian statistics and also bootstrapping and the calculation of confidence intervals for the estimates you calculate. Just because, so with bootstrapping and confidence intervals, so these are values you can get easily from most statistical calculation softwares, and they provide you another level of certainty regarding the existence of specific differences or similarities in your data. And this is definitely very important um, for the inspection of the quality of your data. Yes, you may also spend a lot of time and resources establishing which are the effect sizes. We mentioned that last week, what an effect size is. Um, and it pays off because a wrong estimate of effect sizes may lead to the conception of insufficient designs and to low power. And this is mainly the problem because the more economical designs, so they tend to have also lower power. And the trick is to find ways to keep power high enough without spending too much extra money when conceiving our design, recruiting people, making expensive measurements. Yes, unreliable variables. So this is the problem of variable stability. In many cases, you may be able to measure that using the coefficient of test-retest reliability. So the reliability of variables may be important for you and may help you to understand better so how much your data are liable to effects of regression to the mean, and also so which is the smallest difference between two data points of a specific person, which is too big to be explained by a random fluctuation alone. And so this makes your design much more precise. And this is why, so you should always consider this when constructing your design. Okay, restriction of range. When you are interested in calculating dependencies between different variables, you should take care that the range of the variables you are measuring are acceptable, so that they are not too restricted. So we see here in this example, so in the real data, in reality, you see that there is a moderate to strong positive association between variables x and y. But if you only restrict the values of x, so to 4 and 5, and to the values of y exactly also to 4 and 5, you see that there is no dependency anymore. And so every restriction of range in your variables will lead to an underestimation of possible dependencies between your variables, so be aware of that. Also, so the unreliability of treatment implementation. So depending on the intervention you plan, you cannot control too much how that will be implemented. So if you have to train therapists to conduct your treatment, so some may like it, some may not understand it properly, some may not get enough training so to do that properly. And in clinical designs, so this can be an important source of unreliability and lack of validity. And also heterogeneity within your groups. So it's not an empty exercise in statistics. So to define inclusion and exclusion criteria when defining your experimental participants. So you want to have a certain degree of homogeneity within the different cells of your experimental design, because the homogeneity within the cells will make your task easier to detect differences between different experimental cells. And okay, there is some degree of homogeneity you may not be able to achieve without specific bias and very specific restrictions during recruiting of participants. Definitely, the results you get from college students in reaction time experiments cannot be generalized to the whole population, because so these are very selected, specific kind of people who go to college. And in many of these experiments, so the general cognitive ability and the ability to follow random instructions, so people with a college degree are more used to that. And this, of course, so will change the general results you obtain. Yes, and only if you ascertain that a certain level of heterogeneity is given in your experiment, you have any degree of external validity. But we will address that in the following slides, so please be patient. Okay, we have to talk a bit more about the statistics you use, because so nowadays we have a large collection of tests you may use, and they are quite accessible in different software, so you're not forced to invest a lot of time learning how things work to be able to get some results. And this can be dangerous, because the statistical procedures you use may be based on specific assumptions which will be violated in your experiment. And this is a very important point. So to know upon which assumptions the use of a specific test you may want to use are based, so you have to know them all very well to be able to decide whether you interpret your results or not. And of course, so you will not decide not to do anything with your results after measuring an experiment. So this would be so simply a catastrophe, because we invested many thousands, even hundreds of thousands of euro conducting these experiments. So you have to be sure that you'll be able to do something with the data. All right. Violations of assumptions is kind of common in empirical research, but not all violations of assumptions are equally bad. So some of them may be quite harmless. So it depends on which assumptions are violated and the degree of violation. And for that, so you have to know from statistical diagnostics which aspects of your data you have to check, so to be able to measure these violations of assumptions. And so which impact these violations have on your inference. In many cases, they will have as good as none. And so if this is the case, you're lucky. And if they have some, so you will be forced to acknowledge that in the interpretation of your data when you write a report about that. So you will be more or less forced to disclose any problem your dataset may have. So this belongs to the best practices in empirical research. And you should also invest time in validating your statistical conclusions as much as you can. So by means of calculation of empirical confidence intervals, so with bootstrapping, for example, or if you are more refined, using mathematical Monte Carlo simulations and so on. So all this belongs to modern use of statistics. You may see that statistical books in psychology may never mention that, or only very superficially. But yes, this is because so most of these books are far behind their time. So nowadays, with the help, for example, of the R software, it's so easy to conduct bootstrapping in Monte Carlo investigations on empirical data, even large sets of data, and I mean really large sets of data, so many gigabytes or even terabytes of data. Yeah, there aren't these excuses anymore, so that it's too refined for me. So this is how statistics should be conducted nowadays, because we have the computer power and we have the accessibility to such refined statistical tools. All right, the problem of multiple comparisons is also a big one, and so to address that, you may be interested in pre-registering your investigation. So this reduces your temptation to post hoc conduct further testing and try out different statistical procedures just to get a significant p-value out of your data. Because the problem with false positives is much worse than usually described in statistical books. And so in this study here, a short note on p-value hacking, Nassim Nicholas Taleb, so this famous author from the Black Swan, about other the books. So he shows that in an empirical study, so a Monte Carlo study, so how real data differ from what we actually expect under the the validity of the null hypothesis. So the testing of the null hypothesis is never trivial in psychological experiments because there are all these psychosocial confounding effects, and they all can contribute to generate small differences between groups of participants. And this is exactly the problem. So the only situation in which, under the validity of the null hypothesis, you get a uniform distribution of p-values is when you have absolutely no difference between the groups you are comparing. But it never happens in psychological research. And the problem is, so usually, even if your effects are very, very small in size, the real distribution of the p-values you will get will have this shape. So it will, or actually, so this shape. So you see here the p-values. If the distribution were uniform, you would see just a flat line here, and you see that when you have 5 different tests, or 10 or 15, from which so you search for significant values, you will definitely find significant values, and so the probability that you find something significant is really high. It's very far away from the uniform distribution you usually associate with the null hypothesis. So the simple null hypothesis is never true in psychology. This is a big problem with the use of statistics. And so this guy showed that actually you can address this problem by just using a bit smaller p-value than what is usually done. So instead of 5% threshold, you use 0.5% threshold, and then so you can address these problems much better. So this is just, of course, so a simple solution for a complex problem, and it's not perfect, of course not, but it can help. And so be aware that this is a thing when you are designing your own experiments. Yes, we may proceed now so to understand better so the logics of usual psychological experiments. You will be comparing at least 2 different groups of people, or one group of people measured at least 2 times. You may remember the first slide where I showed all the possible designs you may have in psychology, so more or less controlled, more or less randomized designs. And the tool you use to evaluate the outcomes of these experiments statistically is called analysis of variance. At least, so analysis of variance is the very basic tool you may use so to make some statistical inference regarding your data. So you see some numerical difference between 2 groups. Is that enough to conclude that there is a difference, or is that just trivial and comparable so with a random fluctuation in data? And yes, so we may remember here that actually, regardless of which inferential statistics tools you are using, you are always following the same logic, namely that you are comparing the size of the systematic variation you see in your data, so which are driven by your independent variables or specific combinations of independent variables, and can be causally attributed to your experimental manipulation. Yeah, so this is so the value of greatest interest for you. and it will be compared with random variation. You have to estimate that in your experimental design as well, and this is more or less so the variation of no interest. Why of no interest? Because it's trivial. So it cannot be attributable to your experimental manipulation. And yes, so you see here they build a quotient. And even always when the systematic variation is big enough compared to your random variation, you may conclude that there is a systematic effect of your independent variables or combinations of them over your dependent variable. But if this number is comparable or even small compared to the random variation, so then you may be forced to conclude that there is no evidence in your data of any group difference. And yes, so analysis of variance works in the simplest case with just one independent variable and two levels. So group 1 and group 2. This is the most elementary design you may have, but usually you may have more than just one the independent variable. So you typically you have 2 or 3, so this is not unusual. And beyond the effects of each single independent variable, you may also have a look at specific combinations of these independent variables. So let's say one of your independent variables is sex. So you have male, female, and another one is, let's say, professional success. And you may have also two groups you may select of average individuals and highly successful individuals. So these are also two groups. But yes, so we also know from reality that the most successful male individuals usually get a better pay than the most successful females. And yes, this is a specific combination of your experimental cells. And so the same effect of sex and success may not apply equally, for the two levels of these factors, but they may be specific. And when this is the case, this can be naturally investigated in analysis of variance procedures. So they are just called interaction effects. So you may look at specific combinations of levels of different independent variables and see whether there are some specific effect there. So you have both the effects of each independent variable on your dependent variable and also effects of combinations of your independent variables on the dependent variable. And these interaction effects, they may involve 2 or 3 or 4 or as many independent variables as you have in your design. Not always you have hypotheses regarding these combinations of independent variables. So this is also an aspect you have to consider when forming your design. So which statistical tests you should look at and which ones should not be inspected. So if you don't have any hypothesis, you shouldn't ever look at the data, because you may be tempted to post hoc infer something what is just spurious. All right, so how is the statistics of analysis of variance called? It's called the F-test. And the F-test, as I showed you schematically before, is also a quotient. And in this case, in the simplest case, so you only have, let's say, one independent variable. And this independent variable will code your data as, let's say, so group 1 and group 2. And in this case here, so you have on the y-axis different values of the dependent variable, and on the x-axis you have 4 groups actually. So 4 levels of the independent variable. So you have the x values, so x1 of 4 and x2, x3, x4, so for the 4 different um, levels of this variable. And these squares, they represent for us, so the average level of expression of the dependent variable in each experimental cell. So we have 4 experimental cells, and we see that the average of the group 1 is considerably higher than that of group 2 and 3 and 4. And the question is that big enough so to say that there is a difference between the groups, or is that just trivial? And so to understand that, you have to compare two values. So one is the variability between the averages of the 4 different levels. This is the variance between groups with another value, which is the value, so the random variation, or so the residuals in your model. And they are given by the variability you observe on average within each one of the 4 levels. And this is the variance within groups. And when you estimate both and you also correct them, so for the number of levels you have and the number of observations you have, so you have a computation here of degrees of freedom, then you get an F value. And this F value can be big or small. And how do you evaluate that? So these F values, they belong to a specific F distribution. And we know the density of these F distributions when we are able to establish the degrees of freedom for this distribution. So there is one for the numerator and one for the denominator. And you may also be interested in defining a probability of the alpha error, so usually 5%, but you can adopt other ones. And you know these values, so from the description of the density of the F distribution. And this is associated with a specific value. And every time your F value, empirical one, is smaller than this critical value, so then you are forced to conclude that the null hypothesis is true. Otherwise, if this value is bigger than the critical value, so then you be forced to conclude that the alternative hypothesis is true. And very important when assessing the F value, so the F distribution has 2 degrees of freedom. One for the numerator, as I said, and in the case of the simple design, it's given by the number of levels you have minus 1. So here you have 3 is the degree of freedom for the numerator. And for the denominator, you have the number of levels you have times the number of observations you have minus 1. So then you see here how this works. And so this formula for the calculation of the degrees of freedom, so they are valid when each one of these single observations is independent from each other. There is another case typical in psychology where you see rather that the same people will undergo different experimental conditions. We'll see that in the next slides. But in this case, we are dealing with people who are recruited to perform just one measurement, and they will be assigned to only one group. So the different individuals are completely independent from each other. So then, so this is the formula to calculate the degrees of freedom. All right, so this is the basic case, as I said. And so here we can see the investigation of main effects and interaction effects. And even in the simplest case of interaction, where you have 2 factors, each one of them with just 2 levels, so really simple, you may have many different interaction effects, which may take completely different forms. And they will be also combined sometimes with significant main effects or non-significant main effects. So in the simplest case, nothing is significant. So not the effect of treatment. So treatment is blue line and red line, or the effect of time point. So this is pre-test, post-test. You see both groups are comparable and they keep being comparable in the post-test, and pre-test and post-test are just giving you the same values. So nothing happened. You have no main effect and no interaction effect. But in this case here, so you have still no effect of treatment when you consider both groups together. So there is no main effect of treatment. But you have no. Yes, you have no main effect of you have a main effect of treatment, because so the lines, so they differ from each other, but you have no effect of time because the average of them both is still comparable. Okay, so this is, but you also have here a significant interaction effect. Although, so none of the two main effects is significant. So this is a challenging situation. In these other cases here, so you have a simple effect of time, but no interaction and no effect of treatment. So both treatments work equally well from the pre-test to the post-test. Here you have a more interesting case in which you have an effect of time, excellent, an effect of treatment, so the red treatment works not as well as the blue treatment, apparently, and you also have the interaction effect. And on this side here, so you have once so an effect of treatment, because so the group the red group is performing better than the other one. And here you also have that. But this is also a particularly interesting situation in which so you have a big difference at the beginning and no difference at the end. So if you have an impaired group at the end, and it will improve towards the post-test, but you have here so another group which is becoming worse with the intervention. So this is a kind of a weird constellation. It cannot also be so the other way around, where at the beginning you have no effect and one group will improve and the other one will worsen. So this would have the so the same statistical characteristics, although so the interpretation is of course completely different. And here you see something similar but in other directions. So in many cases the effects of so the main and interaction effects may not be specific enough so that you can still be interested in comparing pairs of data points complementarily. So to understand whether the difference is restricted to the pre-test or the post-test, or restricted to the effect of treatment in the pre-test or the post-test, or not. So to distinguish more or less, so let's say between this case and this case, and this case and this case, so where so once you have only one main effect and the interaction, and in the other case you have two significant main effects and also the interaction. And here you have no significant main effects, but a significant interaction, and here so the other combination. All right. As I told you, in psychology, you may want to have the same participants undergoing different experimental conditions. And this can be done every time when, so the different experimental conditions will not interact with each other. So by a participant solving both kinds of tasks, it will not change the way the participant is solving the task in comparison to another situation in which each participant would only get one of the versions of the task. And because so this kind of design is so typical in psychology, so we have to define them as well. So in this case, even if you have only one independent variable, you still have another systematic effect on your design, which is given by the systematic variance between individuals. So the variance between individuals means that different people will solve the task differently. So let's say with different levels of competence. And this is intrinsic to the ability of single individuals. And this is not random because so it's just a characteristic of each individual. And you may want to distinguish between this and the variance within groups, which is supposed to be just random noise at the end. And so by doing that, so you distinguishing these different sources of variation, you have many advantages. So one of them is that you may spare when recruiting participants, because with only a fraction of the number of participants, you may be able to investigate more complex designs. And also because you are increasing the sensitivity of your comparison by distinguishing between the variability between individuals and the variability which is just so random noise and not systematic in any way. All right, so how's does that work? So you have also an F-test, and the F-test will also be a comparison of the systematic variance with the variance of the residuals. But here, so you'll see that the calculation of the degrees of freedom is slightly different. And yes, so let's move to the characterization of these two kinds of designs. Some designs in which you recruit a group of people to participate in all experimental conditions you have in your design, in comparison to other conditions in which you recruit specific people so to participate in just one of the conditions. Of course, under some circumstances, it's just impossible to put the same people in different categories. So if you have someone with a reading impairment, so this person cannot afterwards participate in the group without a reading impairment. This is definitely then a situation where you have to rely on between subjects designs. And yes, so under some circumstances you may choose between both, but in other circumstances you may not. And there are circumstances in which you should not adhere to a within subjects designs. So let's see why. So in between subjects designs, each participant is assigned to only one experimental condition. Individuals are nested into their treatments. So what does that mean? So the variance between individuals cannot be accounted for in any systematic way, because you don't have any tool to disentangle between random variation and individual specific variation. And you may count on specific residual inflation in comparison with within subjects design, but in some cases it's just unavoidable. So when? So these designs are more appropriate when treatments may interact with each other. So if you just participated in an experimental condition in which there was a lie, and this lie was disclosed at the end. So after participating in such an experiment, you're not naive to that anymore. And if the next condition comes, you will already be prepared that, so probably there will be another lie, another how is that called more properly than a lie? So there will be some deception in the experiment, and of course the participants will not be naive anymore. So this is a typical condition in which, so as soon as you finish one condition of the experiment, you are not eligible anymore so to participate further in the experiment. The experiments tend to be shorter, so if this is a concern, this is an advantage for the participants so that they will be ready with the measurements a bit sooner. And it requires n times k participants, so this means the number of participants per condition times the number of conditions you have. All right. In the other case, so you have within subjects designs, so each participant being treated with every experimental condition, so they will participate in all different experimental conditions. This is typical of a reaction time experiments, so where you will not expect any interaction between conditions, because so the conditions are also pretty similar to each other. So let's say in one condition you are seeing small numbers, and in the other one you're seeing bigger numbers, but yeah, all of them are numbers, so there is no perceivable dramatic difference between the conditions, so you wouldn't expect any interaction effect there, usually. Okay, so the influence of the individual can be separated from that of treatments, so this is an increase in validity you may have by separating sources of variation in your experiment. It assumes that the treatments do not interact with each other and is more efficient when this is true, and is a catastrophe when this is not true. So you cannot be careless about being sure that this assumption is true in your specific case. Experiments tend to be longer for each participant because so you have to fulfill all the requirements for each of the experimental conditions, and it requires less participants, so it's more economical, and this is the reason so why you usually prefer it in psychological designs. Not always, but quite often, for the reasons I just presented to you. And yes, all right, let's move on. So the next level in planning of psychological experiments is given by the so-called mixed effects models. So they are a generalization of the specific case of analysis of variance for more realistic deviations from the assumptions behind simple analysis of variance. So we will, so decompose variance in another way, extended so to account for several so-called random effects in your experiment. So this is a case in which you not only have so the specific variance between individuals, but you may have also the variance between test items or other refined aspects of your design. So you may have the effects of specific institutions participating in your experiment. So let's say it's a multicentric study. So then you have a clinic in Graz, a clinic in Salzburg, a clinic in Klagenfurt. And then, so they will probably not be perfectly comparable to each other. And then, so to disentangle the effects of the treatment from the effects of the location where you're acquiring the data may be a good thing. And this is, can be made in a quite straightforward way using the so-called mixed effects models. So you have another partialing of variance, so it's more complex, and it can accommodate the presence of different so-called random effects. So these are independent variables with which levels are not conceptually defined and small in number, and so specific categories, but so they are just sampled from a population of levels, which is possibly infinite. And yeah, so this is a nice extension of the analysis of variance. So you may see here, so the assumptions put in a clear way for you in the case of the formula. So here you only assume that the random noise will follow a normal distribution with this variance. But here you have not only the random noise, but also so all kinds of random effects as well. So you also expect them so to variate or to be sampled from a population. And there are several extensions of that which so we cannot discuss today. But anyways, so it may increase the statistical validity of your experiment substantially every time that you have to fight against violations of the assumptions behind the simple analysis of variance. So this is a very good alternative to that when you identify problems with violations. All right, so now let's move to the aspects of external validity, so the generalization of your experimental results, because almost never you are just interested in explaining the data you observed, so you want to infer something more general regarding how things work in reality in a more general way. And yes, so to do that, you the first thing you should be able to do is to define the constructs you're measuring. And there is a nice formalization of that, so that all existing constructs you may measure, so they live in the so-called nomological space, and the region in this nomological space occupied by different concepts, so this space can be as highly dimensional as you want. Let's not go down this kind of speculation, but so theoretically, so the different constructs will occupy a specific region in the nomological space, and the relationships of neighborhood or overlapping between concepts will describe the similarities or the associations between concepts. These associations may be causal, but they not necessarily have to be causal. Yes, so why is that a thing? Because even so, if theoretical constructs overlap, so their operationalizations may also overlap, and you want to understand better. So when you are measuring pure intelligence and not just previous experience while playing computer games, and depending on your design, if you use a computer test, which is highly similar to the structure of computer games, it may be difficult for you so to disentangle so these two aspects of your constructs, so the intelligence part and the familiarity with computer games on the other part. Although, yes, so general intelligence should be more or less independent from that, but yeah, so crystallized intelligence is not, but yeah, so you understand the problem here. So you should be able to separate things if you want to understand them. And yeah, so the so-called external validity is about so the generalizability of results to further circumstances in populations. And different experiments may have a high internal and low external validity, or vice versa. And yes, so the kind of strategy you have to adopt to increase generalizability, they may mean that you have to sacrifice a bit of your internal validity under some circumstances. So the both can interact with each other. All right. So here are some examples of threats to the so-called construct validity. So what's the construct validity? Construct validity is your ability to separate between different constructs. So to know which region of the nomological space you are tapping in when you use specific variables in your design. So one problem is when the explanation for the constructs, so their definition is not adequate. And we see this problem in psychology again and again, so that there are several highly similar constructs with different names, but so they measure more or less the same thing. You may agree with me that so self-concept and locus of control and self-efficacy are closely related constructs. And in some cases, so you have this problem because each new author publishing new findings in the literature may name the construct a bit different, and so may add a small detail to an existing definition and give it a new name. And so this can be quite confusing and may lead so to an inadequate explication of constructs, and it may lead so to problems interpreting data. Yeah, construct confounding. So when some measurements you choose, so they are equally good, so to measure one and another construct, so then it's impossible based on your empirical data so to distinguish between them. So your decision to interpret that as one construct and not another is not fundamented in empirical data, and so this is not a good thing. So it reduces the straightforwardness of interpretation. Another problem is when I already mentioned that, so when a whole research field is based on only one specific operationalization of a construct. So let's say you only measure intelligence using non-verbal paper and pencil tasks. So this is definitely a problem because the materials you are using are not comprehensively connected to the concept of intelligence. So there is a lot of intelligence you cannot measure with paper and pencil non-verbal materials, right? So you may give me right here. Another thing is, yeah, so the monomethod bias. So beyond the materials you use, so if you always use the same method, so let's say, paper and pencil tasks without any time limit. So you give people the tests and they have as much time to solve it as they can, or you the opposite. So you always only use tests with a very tight time measurement. So in both cases, you have limitations there regarding the generalizability of results. Confounding constructs with levels of constructs. So inference about constructs best represents study operations. May fail to describe limited levels of the construct that were actually studied. Yes. So when you want to make claims about, let's say, creativity and intelligence, if the association between creativity and intelligence depends on the levels of intelligence, then if you test only highly intelligent people, you may not be able to infer anything about this association among less intelligent people. And so this kind of problem, so it occurs quite often because of sampling problems. So the sample is too limited in comparison to how the theory is formulated. And so this is definitely a problem. So when the treatment is sensitive to the factorial structure, so the structure of measure may change as a result of treatment. change that may be hidden if the same scoring is always used. So what is that precisely? So the structure of a measure may change as a result of treatment. Yes. So let's say you use self-report and you're measuring depression, and let's say so that you have a specific signature in the self-report, so that people talk a lot about, let's say, so negative events or feelings, and if your treatment succeeds, so then people do not talk anymore based on this axis of emotion, let's say from the very negative to the very positive, but the axis of conversation changes to topics of activity, and which may be negative or positive or a mixture of both, but yeah, they are not defined anymore based on the emotional valence of the reports, but on the contents and the variability of contents. And so this is a change you may be unable to identify if you are only measuring the emotional valence of the contents of the self-reports. Yes, so reactive self-report changes is more or less the same. Um, the assignment of participants to specific treatments. So if they like it, they will be more collaborative than if they don't like it, if they feel that, so they have been assigned to the worst condition or to a treatment condition, so they may feel demoralized, and this is a problem definitely. So the reactivity to experimental situation. So the participants' responses reflect not just treatments and measures, but also participants' perceptions of the experimental situation. And those perceptions are part of the treatment construct actually tested. So we have been discussing that last time for so long, so I don't have to explain it again here. So this an interaction between participants and experimental situation, which may lead to completely unexpected results. Experimental expectancies, so depending on what you want to achieve with your experiment. So this will definitely influence the outcomes of your study. So let's say that you proudly invented a new form of therapy. Of course, people being trained in using this therapy by yourself will tend to respond positively just because of their enthusiasm and their perception. So that so this treatment must be good because of your enthusiasm with that. And when otherwise you just give your treatment to other people which are not so personally attached to the quality of it, so they can be more neutral, and so the estimate of the real effect of the treatment will then be more precise, because this effect of your own expectancy, your own enthusiasm will not be there anymore. So it will be controlled for. So possibly one of the other experimenters will have completely different approach to that and a completely different feeling regarding the effectiveness of your experiments, and this will be more representative of how the real effects will be if you implement this therapy on a large scale. Yes, so experimental expectancies determine a lot of what is going on. This is why I mentioned to you last time that we should always have more than just one experimenter the best is to have a few, and so also to vary age and vary gender, sex. It's always a good idea, or quite often a good idea, because so the estimate of the efficacy of treatment will be better estimated. So novelty and disruption effects. Participants may respond unusually well to innovation. Yeah, so we know that from our own research. So every time we recruit people to participate in a new virtual reality environment with game elements, and this highly engaging and it's newest technology, in comparison to a group getting computer version of that without, so stripped of the game elements and with no VR, of course. So there will be more enthusiasm among the participants getting the nicer condition. And it can lead to reactions among participants. And one of them is the compensatory rivalry. So when participants assigned to different groups perceive that so the other group is getting a much better treatment, so then this can lead to participants in the group considered worse to dedicate more, so just to pay back to the experimenter, so being so mean to them and assigning them so to the less interesting condition. So this is the compensatory rivalry. But you can also observe compensatory equalization if these expectations come not from the participants but from the experimenters. So let's say in a clinic you got a new equipment, so to perform some kind of therapy, and because it looks so shiny and because so you read it's new and what's very expensive, people expect that it will work better than the older equipment. And if you're running a validation study, so an efficacy study there, you may see that the staff realizing that some participants got the best equipment. So then they are nicer, they give more attention, and so they try to compensate for the disadvantage given to the other group. And so this kind of perception may invalidate all of your results. So you should be able to measure that. So compensatory equalization, compensatory rivalry, as well as resentful demoralization. So this more or less the opposite of compensatory rivalry. So the people in the group perceived as more boring or less important or just a control, they may then not put any effort anymore in participating in the study because they perceive themselves as in a disadvantageous situation. And yeah, so they may also decide to jump off of the study. So you may see that so the drop off in the control group may be under some circumstances higher than among the treatment group, just because yeah, people see that yeah, I will not get any benefit of that anyway. So this too boring. I will give that up. So this is the so-called resentful demoralization. There's a treatment diffusion. So if participants belonging to different treatments talk to each other, so they may exchange valuable information and it may feed their expectations, so regarding which treatment is better, what people are doing with us, so what can I expect from what I'm training. And it can even lead some people so to want to participate in both groups or to change groups just because of things they heard. And so this can be a big problem for the interpretation of results. And it happens every time that so you are in an institution and you have two or more conditions running in parallel. And so participants have the opportunity to talk to each other. We see that also so across experiments, so among groups of participants like psychology students who know each other. So they may comment on the experiments they participate, and so in this group, so it's nice. In the other group, so the reward is higher, and so this can also lead to systematic bias in the recruiting of people. So for experiment. Yes. Now we may talk about threats to external validity. So the external validity is our ability to generalize empirical results, so to further aspects of reality. One problem is when you may not distinguish between the impact of specific experimental unities and the effects you observe. So I can give you some examples of that. So these unities can be, for example, the experimenter, him or herself. So if you are the only person running your experiments and you know your hypothesis and you explain the task to your participants, there is a confounding between your expectations and what you have in your experimental design. And we will never be able to separate both if you are the only experimenter in your design. Another situation is which, so you have, let's say, a specific kind of stimulus, and in every study about a specific topic, you only have this same stimuli. And this is a problem because so you have no clue about the generalizability of these results to other similar stimuli which belong to the same category but were never used in investigation. So this happens quite often in the literature. So interaction between causal relationship over treatment variations. So an effect found with one treatment variation might not hold with other variations of that treatment. So let's say in a specific kind of therapy. So if you have a generical and another version of some medicine, so the results you know from the literature, from brand versions of the treatment may not react exactly in the same way as the generical medicine. So you never know if you only use so the brand medicine. Interaction of the causal relationship with outcomes. So an effect found on one kind of outcome observation may not hold if other outcome observations were used. Yes, exactly. So you may observe that some effects, let's say an intervention towards increase of empathy, so that it will produce measurable effects on implicit measurements of empathy, but not on explicit ones. So if you ask people, so did you perceive so any change in your empathy from the first to the second time point? So all people will say, no, I didn't perceive anything. Or definitely, yes, I perceived a big difference. And when you use an implicit measurement, which is beyond conscious control from the participant, you may see the opposite results. And so it's always a good idea so to have different measurements which imply which involve different outcomes, so different outcome measurements. So to be sure that the results are robust and that they are as expected and not an artifact of one specific realization of the experiment as you planned it. Yes, and I believe, yeah, so the same regarding settings. So it's just a variation of the other one. Context-dependent mediation and explanatory mediation of a causal relationship in one context may not mediate in another context, for sure. So a typical example. So when you compare different countries, so in many countries, you have as good as no alcohol drinking people. And in other countries, you have most of the adult population drinking some alcohol, particularly when you are under increased stress and particularly in times of uncertainty. And of course, alcohol consume will be a relevant predictor of what is going on in people who typically consume alcohol, but these results have less value or no value in a population where nobody consumes alcohol. So this is the point with this. And so different predictors will have different values depending on the populations you are addressing. And you have to be sure that all the mediation factors you are interested in, so that they still hold, they still have the same function in new populations you may be interested in the future. All right, so this is more or less it. So here I have two specific examples of interesting, easily readable literature for you, where you can see the effects of experimenter and the effects of observers on the results you get in clinical studies or even in daily living behavior like skating. And will be quite enjoying for you, so having a look at these papers. Yes, here we also have once more, so to conclude today's presentation, a list of three quite famous experimenter and observer effects. So the first one is the Rosenthal or Pygmalion effect. What does that tell us? So expectations of the experimenter change the way participants react, and so how people will behave in your experiment. This is why, so you should always as possible so have many experimenters and also so have different kinds of experimenters, so just to have the different individual expectations cancel each other out, because so they will forcefully go in different directions, right? So then you make control for the effects of the Rosenthal effect. Another effect is the effect of being observed. So when you know precisely that your behavior is being measured and that it may have consequences for you or for your self-image and so on, you will also react differently. And so when you tell people that their behavior is being monitored, they cease to behave in a natural way, which is characteristic of situations where they are not being under so much scrutiny. Yes, and the last one is an effect of mistakenly taking some general properties of your participants and inferring values of other properties of your participant. So this is called as the halo effect, and this halo effect describes a trend people have, so to connect some physical attributes of people to other hidden properties. So people just assume that older people have more experience in a specific design. And so if you have an older doctor, usually you feel more confident that he or she is an expert than if the doctor just looks like a freshman from the university. And there are also these effects regarding attractiveness or the way people express themselves in interviews. So this can be rehearsed, right? And you can convey a much better impression about your loquacity and your cognitive abilities by just rehearsing desirable reactions, and you may leave a very positive impression about yourself and your competences, and then you get hired, and the day after, so there is a disappointing behavior, because so all of that was just not for real. But so people tend to attribute visible signs to invisible properties of people or characteristics of people, and these may be important in your designs as well. All right, that's it. So I will just skip this last one, and so we can go to the conclusions. In the experimentation with humans, there are numerous confounding effects. It's impossible to get rid of them all in one design, so this is why you should always combine different designs, different methods, different materials, and so on. Different experimental designs fulfill different purposes and complement each other. A clever design will control for the most important confounding effects and produce stronger evidence, which effectively contributes to the literature. Randomization, always as possible, so distributes spurious sources of variability equally across conditions, so it's desirable every time where it can be applied, it should be applied. So when possible, employ experimenters naive to studies' aims, because of all these psychosocial effects. When possible, employ more than just one or two experimenters to collect data. We discussed the reasons for that last time. So choice of most appropriate statistics is not trivial. I hope I conveyed this message to you. Then experiment with humans is a social interaction and works under its psychosocial rules, which can be quite complex. And yes, so internal statistical construct and external validity dictate the strength of your findings and scientific progress. So for you to know whether you are just wasting your time conducting a study or doing something important, so these are the criteria, so to judge your efforts, right? Thank you very much for your attention. Thanks for your patience and for your understanding for me not being with you today in person. Okay, thank you. Bye-bye.